Hello, Mr. Kitchen, Cobleskill, Richmondville High School Physics. In today's video on Ohm's Law, we take a look at what is probably the most fundamental relationship in terms of electric circuits and calculating the values in these circuits. A German physicist by the name of George Simon Ohm, he was doing experiments where he was changing the potential difference. He was measuring the current in a circuit. And what he found was that every time he, say, doubled the potential difference or the voltage, the current doubled. So if we took the ratio of those two, you ended up with the same number all the time. And it would be different from circuit to circuit, but for a given circuit, the value was the same. So he called that number resistance, and the resistance represents the opposition to flow of charges in an electric circuit. In a sense, it represents how difficult it is for electricity to get around the circuit. So now we have or are able to build a formula that uses these three fundamental quantities: potential difference, current, and now resistance. So let's talk about these three quantities conceptually. They're the fundamental quantities that we have in electrical circuits. We've got V, that stands for potential difference, although we often call it voltage. And it's related to something called EMF. It's very close to that. We don't have to get into the details of what that is, but when you think about voltage, it is perfectly fine if you want to think of it like a force. This stands for electromotive force, and it's proportional to the force that's pushing the electrons through the circuit. When we set up a circuit, there's an electric field that's formed inside the wire, and that wire pushes on the electrons. So the more potential difference we have, the more force or the more push we're going to get on the electrons. Current is flow. It's like water from a faucet. If you open the faucet a little bit and it trickles out, that would be a small current. And if you open up the faucet all the way and the water is gushing out, then we have a large flow, a large current coming out of the faucet. And then R, the resistance, well, that blocks the flow of water. I mean, you could shut a valve all the way off and there's no current coming out. There's no water coming out of that faucet. Then you can open it a little bit, and when you open it a little bit, there's high resistance to flow, so the water comes out like a trickle. And of course, we can open the valve all the way up, and when we do that, there's very little resistance to the flow of electricity, and we get lots of current. So when we're thinking about those three things in electric circuits, it's often handy to think of them in terms of their analogous quantities. Now, generally we write Ohm's law as a formula, something like this. This is what's written in the reference tables, R equals V over I, or we can write V equals IR. I put a box around the resistance because the resistance is often a constant. So in this formula, R stands for resistance. We can see over here resistance could be measured in volts per amp, and the volt per amp is defined as, now this is the Greek letter omega. It kind of looks like a horseshoe, and the unit itself is the ohm. Omega is the symbol that we have for that, and of course we do that to honor George Simon Ohm. Resistance is constant in these circuits at constant temperature. So we look at the formulas, we don't see any temperature dependence or temperature term. It's kind of complicated to put that in there, and it varies from material to material. So because you don't see it in there, the assumption that's being made is that temperature is being held constant, and therefore resistance is constant in that circuit. And then finally, you should have some idea, as temperature increases, resistance increases. Now, as temperature increases, atoms and molecules are always vibrating, and as temperature increases, the vibration, the amplitude of vibration gets larger and larger. Well, as the atoms and molecules vibrate more, it makes it more difficult for the electrons to find a clear path to go through that circuit. What happens is they hit something and they bounce back a little bit, and then they go forward and they hit something else. So as temperature increases, the atoms and molecules are vibrating more. As the atoms and molecules vibrate more, it makes it more difficult for the electrons to flow through that circuit. Now here's an alternative way we can take a look at Ohm's law. We can use a mathematical formula, or we can take a look at a graph, in this case a graph of potential difference versus current. And we're taking a look at two. The first one is for a resistor. We're assuming that resistor is at constant temperature. I've plotted V versus I, and in this case the slope of this graph represents the resistance, and we can see the slope is a constant due to that constant temperature. So when we get a graph like this, we say, okay, yep, the slope is constant, and therefore the resistance is constant. Now, if we take a look at a light bulb, when we send more and more electricity through the light bulb heats up, and so the temperature increases. The slope is still resistance, but if you recall from our work in mechanics, if we want to find the slope at a point on a curve, what we have to do is draw a tangent line to that curve. So we draw the tangent line, and we get a small slope over here. When the current is larger, then we get a steeper tangent line, a bigger slope, a bigger resistance. So what we can see is that as the current is increasing, the resistance is increasing, and that goes right along with the increase in temperature that we talked about. The increase of resistance is due to the increase in temperature. And I want to end here. I've got a simple example for you. I'd like you to calculate the resistance for the circuit that I've diagrammed here schematically. I want you to show me formula substitution and result underneath this circuit diagram. What we have is a 12-volt battery, and we have an ammeter here that's measuring 3 milliamps of current. And when I come around and check the notes, what I want to see is how much resistance does this resistor have to have in order for this circuit to obey Ohm's law.